today we are going to do section 7.1 on page 832, the second order differential equation. What that means is that you have, let's look at the definition at the bottom of the page. Okay, a second order linear equation is something you start with, you have y double prime, that's the second derivative, okay, and then y prime, and then just y, and then it equals to no y's, okay, just x. And then it has coefficients in terms of x. Now this function y is only in terms of x, okay, we're not talking about 3D anymore. And we're just doing the same old thing we always did. So y is a function of x. It has this particular equation that it satisfies. If that is true, then we call this thing is a second order differential equation, and then it is linear. Okay, linear means there's not something. Well, linear means that. And anyway, and specifically, if the final term r of x is identically equal to 0. See Rx, so which means it is not there. Okay, there's no, it doesn't equal a constant or any x or nothing. It's completely 0. If r of x is completely 0, then we call this thing a homogeneous linear equation, and that's what we're going to be doing today. So let's with that, please look at example 7.1, where you classify whether something is a second order equation or not. So please do that as part of your homework. Next, let's go to page 834 and look at example 7.2, where you verify some solution. So what you do is just take the solution, and then you take the first derivative and take the second derivative and plug it in and see if it works. So please do example 7.2 as part of your homework. And then now we're on the following page 835, where there's the theorem 7.1 superposition principle, where it says that if you have y1 and y2 are both solutions of your linear equation, okay, and so that if they're both solution, then some kind of a constant adding together, well, any constant, multiply them and then add them up like that is also a solution. That's just, and the reason is because derivatives are very amenable when it comes to constants and addition, right? You just add it in and it all works out. So it's, I think that's pretty obvious actually. And so, so we'll accept that, and then know that if you can find two solutions to the differential equation, then any constant multiplied and add up of those two solutions will also be a solution. So with that, to verify that, please do example 7.3 as part of your homework. And now we are now on page 836, where we are going to talk about what linearly dependent means. Linearly dependent is when two functions are somehow multiples of each other. For example, let's say you have x. Say if you have a function x, okay, and then you have a function is 3x. These two things are linearly dependent because one is the multiple of another, or some kind of a way to multiply them together. Now the two functions, the exact definition goes something like this. Look at theorem 7.2. That is, two functions are said to be linearly dependent if either one of them is identically 0, or if f1 equals to cf2 for some constant. Functions that are not linearly dependent are called linearly independent. Well, most functions, of course, are linearly independent. It's just if your function just happens to be the multiple of something else, so that they're linearly dependent. So to see some examples of that, please do example 7.4 as part of your homework. Next, let's go to page 837, where we consider the theorem 7.3, which is the general solution. Now, this is important, and so please remember this thing, even though it's not. Well, anyway, so if you have y1 and y2 are linearly independent, so they're not multiples of each other, okay, and they are solutions to a second-order linear homogeneous differential equation. Second order means the derivative goes up to the second derivative. So if that is the case, if y1 and y2 are the solution for these differential equation, then the general solution, which is given by some kind of constant, you add them up and then multiply by some constant, any constant, then the general solution is also a solution to the differential equation. But there is more to it than that. This also says that this is the only possible solution for that differential equation. That is, if you find two linearly independent solutions to a differential equations, then you're done, because all other solutions are just some kind of a constant multiplied and then added together of those two things that you found. Now, we're not going to prove that because that is more difficult, but but we are going to remember that as we find more solutions. That is, all we have to do is find two independent ones, and then we're good to go. So, and now in the meantime, let's practice writing the general solution. That's example 7.5. If you have two y1 and y2, okay, what is the general solution? The general solution is just you slap C1 on one of them and C2 on the other one, add them up, and that's your general solution, as it says in theorem 7.3. So please do example 7.5 as part of your homework. Now let's go to page 838, where we're going to solve this particular second order equation that we've been talking about. Okay, so the equation, as we remember, the second order equation, homogeneous and all that stuff, linear, is in the form of a y double prime, the second derivative, plus b y first prime, first derivative, and then just y times a constant, and that equals to 0. And that's our equation. And that's the only equation we're going to solve, because, well, differential equations are hard. Okay, we have to do one type at a time, and basically, and count ourselves lucky when we can even find a solution for it. So the first thing we're going to consider is this particular solution, y equals the e lambda x. You might think, why? I don't know, we're just walking around trying different things, hoping that something works. That's it. So let's try this one, see if it works, and what would happen if it works. Let's say this is a solution to our second order linear differential homogeneous equation. Big long name. But anyway, so let's plug this thing in there, okay? And that is, we'll plug the e equals the lambda x into this equation on top. Take the derivatives and stuff. Being that is e, so we'll plug it in right here. Now, being that is e, the derivatives are easy to do. So what we have, as you can see in your book, is you plug it in, okay? And then very soon you end up being, you come up with this equation down here, where you have e lambda x, and you can factor it out, and you end up with a lambda squared plus b lambda plus c, which means that if this particular equation equal to 0, then this whole thing will equal to 0, and therefore this is a solution. So what we're going to, so as long as lambda satisfies the quadratic equation, then we're good. Okay, we just have to solve for lambda, and then we have the answer to our at least one answer, maybe more, being that the quadratic equation has two roots, right? So we'll have two solutions for our differential equation. And then remember that we just mentioned that if you have two independent solutions, that's it, okay? All other solutions are in the form of those two solutions by adding them up and multiplying by some constants. So then we're done. So which means that this is good. We have, all we have to do is solve for lambda. Lambda is a constant here, by the way. So as long as we can figure out what lambda is, we are home free. Okay, this particular equation even has a name. It's the characteristic equation of the differential equation. And of course, to solve it, we use the good old famous quadratic formula. And so lambda is easily calculated by this equation, right? So now we are good. We have two lambdas, and then the two lambdas will be independent. They're not, what was it called? I can't even remember what it was called. They're linearly independent, I think. Anyway, so then you can just, then that's your solution for your differential equation. However, we do have to worry about certain details, okay? First, That's because the quadratic equation might come out with two distinct roots or two identical roots, or even two imaginary roots. So we'll consider each case and see how that might work out for us. First, let's pick the easy one. If it comes out with two distinct roots. If it comes out with two distinct roots, then the general solution, okay, we solved it, equals to lambda 1 and lambda 2. So the general solution, as we saw a little earlier, is just some kind of an addition and multiplied by constants. And anything that looks like that will be the general solution of our differential equations. So we are all good to go. All right, that's for two distinct real roots. Now, next question is what happens if we have a repeated root? Now, the repeated root, then lambda equals to two things, right? So so now what? Now what we're going to do is but we want two solutions and there's only one. So what we're going to do is we're going to consider the next thing. We're going to consider y equals to e to the power, x, y equal to x e lambda x. If we do that, then we notice that this thing, if you plug it in, also works. And the reason it also works is because lambda is now is a double root, which means in that case b squared minus 4ac equal to 0. Right, so which means lambda equals to minus b over 2a. So if you let x choose this new solution where x equal to this thing, x times whatever, then and then you plug everything in, you notice that here's where we are plugging it in. Now please do this part of the algebra as part of your homework. Or you can just stare at it right now, I guess. Well, either way, make sure you see why this is working out. So when you plug it in, you notice that you end up with the first part, the equation being that lambda is a solution to the characteristic equation. The a lambda squared plus b lambda plus c will be equal to 0. But what about the second part? The second part is, remember, lambda equals to minus b over 2a. Okay, because it's a double root. Now, if that's the case, you plug in the second part, that also equal to 0. So the whole thing does equal to 0, which proves that this is a solution. Now, you might wonder, where did this come from? How do you come up with that? You just sit around, and the same way you come up with this, you sit around, you try different things, and then something suddenly worked, and you're lucky. You know, it's kind of like bargain shopping. You look around all this stuff and find something you like after looking for a very, very long time. So that's how this will come about. And as you can see, this does work. And so please do this part. I would like you to do this part of the algebra as part of your homework. Where is this? We are on page 839. Okay, so please verify this part. Okay, starting from here all the way, verify that the y equal to x e lambda x does work as a solution. Right. So please do that as part of your homework, and I will write it down here in the notes. As a result, then, the general solution for situations where the characteristic equation has two identical roots, then the general solution will be written like this. That is, the first one is the same as before, e to the lambda x. The second one will be x e to the lambda x. And that all works out nicely. So next, let's look at the complex conjugate roots. There is a third possibility, of course, is what if the quadratic equation has two imaginary roots? Well, if that is the case, then we are going to write it the same way. We'll have two imaginary. Let's say the answer is the two imaginary numbers. Okay, right. And anyway, so the imaginary numbers, we'll call it lambda 1 equals to alpha plus beta I, and lambda 2 equals to alpha minus beta I. Now remember how the beta I comes from, okay? That comes from the square root when you take, because lambda equals to this is the quadratic formula right here, right? If the square root, if what's inside the square root is negative, then we'll just take the square root and then slap I on there. Those are the two answers. And that's how we come up with the lambda equal to values. If you can't remember exactly how to do the complex roots, please Google and figure it out. You just slap I on there and then proceed as usual, basically. But anyway, so lambda equals to these two things. But what does that even mean? Well, we don't care for now, okay? We'll just slap it on there, and then let's see. So just like we did before, we'll slap the lambda equals, which now equals to some kind of complex number. And so let's look at the next page, all right? Now we're on page 840 on top, where we have E. Okay, so here are our solutions. E is alpha plus beta I, e to the alpha plus beta I x, that's our lambda, and then the negative one, e minus beta I x. Okay, so we have two of them. So as a result, once we have done that, then of course the general equation is equal to this, right? Now our lambda has I in it. But otherwise, it's the same principle. However, now we have a problem. We got I in the solution. We don't want I. Okay, that's the imaginary number, and we have never touched it in calculus, and don't wish to do so now. So we need to get rid of it. Now, to get rid of it, however, we haven't learned enough complex numbers or complex analysis to do that. So we're going to borrow some formula from complex analysis that we haven't had yet. So when you look at this formula and that we're going to use, do not be surprised that you've never seen it before. That's because you haven't. I mean, that you're puzzled, you don't remember it because you haven't had it. Okay, probably. So we're gonna do this, but we're gonna take this thing and run with it for now. We'll just believe that this is correct without being proved. And this thing is called Euler's formula. Euler is the greatest mathematician of all time. So now this is Euler's formula, and we're gonna plug it in, and with his help, get rid of the I. Now remember that we have the general solution. Okay, here's our general solution. Right, and then so we're gonna manipulate, do some algebra with this using this equation, which is EI theta equals to cosine theta plus I sine theta. Whereas remember, I is the complex number, which is the square root of -1. So remembering that, we're gonna manipulate this thing. Okay, first we are gonna factor this thing out a little bit, factor the E alpha out, that's the real part. Let's factor it out, so we got here, and then we are going to plug in the EI theta formula into the complex part. So theta, so now beta is the new theta, okay? So we're gonna plug it in, and we end up with this pile of stuff. So E beta Ix is gonna be the cosine beta plus I sine beta down here. See, cosine beta x plus I sine beta x, and it's the same with the negative beta one, same thing. So we get a bunch of betas now, but we still have the complex number. And how's that going to help? Well, we'll look a little further. So now once we plugged everything in, and so then we will clean it up a little bit. Let's see, where's the cleaning? Why is my camera not focusing? There we go. Okay, so we clean up a little bit, right? So we still have the I there. Right, and then remember this C. What are C? The C's. C1 and C2 can be any number, and it'll still work. So we'll pick C1 and C2 to both be 1/2. That will get rid of the second term, the I part, and we get this one solution, which is E alpha x cosine beta x. That will be our one of our solutions, and being that C1 and C2 can be anything, so we choose them to be 1/2. And then, so next, we isolated one of them. The next thing we're going to do is we're going to choose C1 and C2 equals to minus what I over 2 and I over 2. So when you plug that in there, then C1 minus C2 is going to be, then it's going to be -1 or something. Minus I, okay, and then times I, that would become +1. So that's how we magically got rid of the I, the imaginary number. So then So then we have, and also C1 plus C2 at that point equal to 0. So the first part becomes 0. And then we have the second part. So that here's the second solution is E alpha x sine beta x. So now we have two solutions. And what are the two solutions? The two solutions will be the general solution of situation where the characteristic equation has imaginary roots. Then we will have the alpha and beta situation where alpha and beta are the imaginary the two imaginary roots. Alpha and beta are the representation where of the two imaginary roots. See, alpha plus beta I is one root, alpha minus, see this line, alpha minus beta I is the other root, and then the solution for your differential equation will look like this. Now, having said this, I ask you, our proof here is somewhat cryptic because we're not familiar with the complex numbers, right? And we don't even know the Euler formula, we just borrowed it. So all this might feel a bit odd, but to convince us that this does work, all you have to do is plug in these two solutions, plug this thing in, confirm that these two are indeed the solutions in the case where the roots are imaginary. So please do this, okay? Verify that this solution and this solution is indeed the two solutions for the differential equation. Where's our equation? It's not on this page, but it's AX is on the previous page. Right, here's our solution. So please verify that the complex solutions, it does still work for this, okay? Once it works, then that's all we care about. We'll ignore the fact that we have to go through the complex route to get it. Just plug it into this linear equation, plug it into the differential equation to make sure it works. So please do that as part of your homework. And you might notice that the solution to these differential equations, they're sort of random. It's kind of like you're running around rummaging and finding a solution, and if it's I, then you rummage some more and then found some other equation that's called Euler's formula and sort of beat it into shape. Everything is somewhat random instead of systematic like we're used to in math. But it doesn't matter if it's random or systematic, it works, okay? What works is what matters. Therefore, in math, the end justified the means. So then that's that. And so let's go to the next page, page 841, where we see what we have done in the chart. So page 841 states that we have the solution for all of them. To solve the differential equation, linear, second order, homogeneous, all those things, right? We have, if you have two distinct real roots, that solution, the first one. If you have one repeated root, then the solution, there's a solution. And then if you have complex roots, that's the solution. And you just go by this chart and do all your homework that way. So with that, please do example 7.6 as part of your homework. And there seems to be 6 problems in one example. Okay, so please do that. The same with example 7.7, 7.8, 7.9, and 7.10. Please do all of them as part of your homework. It's very similar to doing differentiation in the old days for the initial value problems or the boundary value problems. It just means you plug in some number and you have to solve for C1 and C2 or something like that. Okay, so that marks the end of this section. Now for homework, please do problems on page 847. Please do problems 13, 17, 21, 25, 29, 33, 37, 41, 45, 47, and 51. And I won't be talking about any of them because they are all a matter of you take the derivative and then, of course, you have to calculate the roots, the lambda, and decide which formula to plug in, that sort of thing. Okay, so you shouldn't have too much trouble with that. And that marks the end of this video.